Newton's second law of motion has to do with air resistance, has to do with gravity, and terminal velocity. And I'm going to show you those 4 demos, and you should be able to predict what's going to happen with each if you understand the second law. First one is this hammer. Now let me ask you this question first of all. Do heavier objects fall faster than lighter objects?
Yes.
I heard no, I heard yes. Pretty common response. Obviously the head of the hammer is heavier than the handle. If I were to drop this, like so, I want you to predict what will happen as it falls. Will it fall like it is? Will it go head down first? Will it go handle down first? How many say it will fall like I dropped it? How many say it will go head down first? Almost everybody. Okay, well I won't ask about the handle then. The next question has to do with this book and a piece of paper. The book and the piece of paper have roughly the same shape, not the same thickness of course, but the same shape this direction. And I'm going to drop them both from the same height at the same time. How many think the book's going to hit first? Okay, how many think the paper's going to hit first? Jeff is the only one. He's standing out there looking different. That's good. Okay, let's see what would happen if I changed it to 2 pieces of paper, both the same piece of paper, just one's crumpled and one's flat. I dropped them from the same height at the same time. How many think the crumpled paper is going to hit first? Okay. Remember, not everything in physics is like you might expect it. Some things go exactly opposite from what you would expect. All right, I have another little demonstrator here, kind of a cool little gadget that illustrates Newton's second law. And what I have are 2 steel balls here. One is held on by this rod. The other one is resting on this platform. When I throw this lever, the lever will go, the rod will go this way. It will knock that ball that direction, and it will allow this ball to drop. And that will happen at exactly the same time. One ball flying out that way, one ball dropping. I could duplicate the exact same experiment with a gun. I won't do that for safety reasons and the fact that I'll probably shoot someone in Miss Salzman's class. But if I took the gun and I took an identical bullet to one that was in the gun and I dropped that bullet at the very same time that I pulled the trigger, okay? Pull the trigger and drop the bullet. That bullet will fly out that way. This bullet will go downward, obviously, for gravity. Question is, which one will hit the ground first? How many think the one that's just dropping will hit the ground first? How many think the one that's being shot out will hit the ground first? And you're just taking wild guesses here, aren't you? Well, I'm just going to go against the crowd. All right, the last one has to do with these washers. This demo got a little screwed up here, but the washers are supposed to be evenly spaced, 1 foot apart. And I'm going to drop them into this pie pan so we can hear the sound that it makes as it hits the pie pan. The prediction I'd like you to make is to tell me what that sound will be like. Will the sound be constant? Will it start slow and go faster? Or will it start fast and go slower? How many think it'll be constant?
Wait, what are you doing?
I'm going to drop the washers, that string of washers, into the pan, and each one will hit. How many think the sound will be constant? How many think it'll speed up? How many think it'll slow down? Newton's second law of motion. Lots of words up there. Let's see if we can absorb what that's saying. A net force acting on an object causes the object to accelerate in the direction of the force. Okay, let me put that into common English. A net force acting on an object. Aren't I mean? Causes the object to accelerate in the direction of the force. If I increase the force, she accelerates even farther, even faster. I'm so mean. I really am. And there's actually a math formula that goes along with this. It goes force equals mass times acceleration. If you know the mass of the object and you know how much it is speeding up, how much it's accelerating, you can tell me the force that's applied. Okay? I used my same foot, had the same mass, but the second time I kicked Megan Lynn's desk, I kicked it with greater acceleration. So I applied more force. And lo and behold, she went further. Okay? A net force acting on an object causes the object to accelerate in the direction of the force. And when we know this kind of thing, when we know the force, the mass, and the acceleration, we can make all sorts of predictions. Like I think you know what's going to happen when the truck hits the little red wagon. Okay? Even if they're moving at the same rate of speed, they're accelerating the same. This doesn't have nearly as much mass as this one, so it's going to have a lot more force going this way, and one of them is going to get crunched, right? The mass of the car, whether you get hit by, a little VW Bug or you get hit by a semi, it's going to make a huge difference on what might happen because of the mass. I double the mass, I'm going to double the force, okay? In sports, there's only so big you can make yourself, so you have to learn how to be faster. So, in football, in virtually every sport, you learn how to increase your speed, because if you can double your speed, you can double the force. You might see sometimes that you see a player hit another player, and they don't look like they're moving that fast, and they hit that other player, and that player just goes flying, right? Okay? You're like, whoa, they just went flying across the field. Well, that's because they had a lot more mass. Greater mass into less mass, like this example, that little wagon's going to go flying or get crunched, one of the two. Okay? Now, in honor of Sir Isaac Newton, we measure force in newtons. So when you do some math, which you will do on your homework, your mass is going to be measured in kilograms, kg. Okay? You might make a note of that somewhere. Your mass is going to be measured in kilograms. And in this formula for acceleration, we always use meters per second squared. So all you have to do is take that acceleration number and multiply it by the kilogram mass number, and you get a force. Whatever that number is, you could write this label on there. You could write kg.m/s squared. That's one way to label force. kg.m/s squared. Well, let's think about it. Where did that come from? Mass, kg, times acceleration, meters per second squared. You see how we got the label? Came right from what we did in the formula here. Because that is a lot to write, instead of labeling our stuff kg.m/s squared, we honor Newton, because he was the one behind all this, with a big capital N. So the N is used to, as the abbreviation, to label the answers. Got it? You should likewise be able to solve for different things. Maybe I'm giving you the force and the mass, but I want you to solve for acceleration. Back up here. So force equals mass times acceleration. So like if the mass is 2 kilograms, my foot was 2 kilograms, and it was accelerating at 5 meters per second squared, what is the force? 10 what? Capital N. I could label it kilograms times meters per second squared, but N is a lot simpler. But I may do just the opposite. I may say the force is 20 newtons and the person has been accelerated at 5 meters per second squared. Can you tell me what their mass must be? Okay, so you figured out 5 times something equals 20. 5 times 4 equals 20. And you're right. It would be 4 kilograms. Okay? But just like before, you should be able to put this in that little circle thing. What goes where?
The F goes on top and then the M and the N on top.
Like that. Okay? That way, if I'm asking you to solve for acceleration, you know you're going to take your force number and divide it by mass. If I'm asking you to solve for mass, you're going to take your force number and divide it by acceleration. So you should be able to solve for any one of those things. Okay, back to this one. Any questions on Newton's second law? This is what the law says with regards to force, mass, and acceleration. But there are other factors that affect the speed of objects. When I'm looking at how fast an object can go, whether it's going that way or that way, there is a big factor. That big factor is gravity and air resistance. Those are the two biggest things. Good. You guys are all over this. Air resistance and gravity. Gravity we'll talk about in a second. But air resistance is a huge factor. Air resistance is the force that air exerts on any moving object. Okay? And there's a question on one of these assignments about just that, about moving objects and air resistance. It says, what three things determine how much air resistance you will encounter? And the three things are
Speed, size, and shape.
Speed, size, and shape. Let me illustrate each of these here for you. Okay? You all know that when you stick your hand out the window of the car going 20 miles an hour versus 50 miles an hour or 75, you're going to feel a lot more resistance. The faster you're going, the more resistance you feel. And the reason for that is, as you go from point A to point B, you step into new space. There was something occupying that space. That something was air. The faster you move, the quicker the air has to get out of the way. Okay? So when I run past you at lightning speeds, that wind that you feel is the air that was in front of me moving to the side. If I can move at, I don't know, the speed of sound, that air is going to have a harder and harder time getting out of the way quickly enough. And I end up with like a cushion of air in front of me. And to force my way through, it gets harder and harder to do that. That air has to get around. And that leads to a whole other discussion in a little bit. We'll talk about that. But the faster you move, the more air resistance you'll encounter. The greater the size, the more air resistance. Obviously, this double-decker bus is bigger than the little sports car, so it's going to have more air resistance. Nathan?
So if you were to do something big versus something small, could you experience the sound feeling faster than
I don't know the answer to that question. Yeah.
Well, since of the friction of the air going past you, could it catch on fire?
Yeah, and that's a good point. We'll get back to speed. You're going down the freeway, you know, you put your hand out like this and you feel a lot of air resistance. You turn it this way, the shape makes all the difference in the world. It cuts through much more easily. But if you were to stick your arm out the window of, oh, I don't know, the space shuttle upon re-entry into the Earth's atmosphere, you're going to be moving at such a high speed that not only will you feel your arm being ripped out of the socket, probably being pulled back and torn right off of your body, but the wind, the air is moving by so fast that it's creating so much friction that it heats it up. It's going to torch your arm. It's going to be this little brittle stick of, you know, flesh when it hits the back of the shuttlecraft. Okay, so you don't want to do that. And as you know, the space shuttle upon re-entry has had some problems with the tiles, and one of them may have fallen off or gotten cracked. And that air is moving so fast and causing so much friction and heat that it melts the body of the space shuttle, causing it to fail, and the whole thing can blow up on entry. Yes?
Well, since it's going so fast, when they deploy the parachutes or something like that, wouldn't the parachutes catch on fire?
By the time the parachutes are deployed, that's almost on landing. Okay? Parachute, the way the space shuttle is supposed to work is like a glider. So it comes in and it uses the belly side that has a lot of tiles on it to take all that heat, and they heat up, get super, super hot, and then it slows down as it enters in through the Earth's atmosphere. And then as it approaches for landing, it does this real long approach over a long, long way, over states coming in. And it's slowing down as it's doing that. It's using its engines to slow down. And the last thing is as it comes down, it deploys its parachutes to get it down to the final speed it needs to brake. The parachutes aren't used for, it was the same way with the old capsules, okay? They would basically come down like a rock, and the bottom of the capsule would get super hot as it would fall. And then partway through its fall, then they would deploy the parachutes. Parachutes aren't effective up real high because the air is too thin. We got to deploy them lower down, closer to the ground. So it slows it down the last bit. Okay? But we're going to look at how falling objects will slow down. They will reach a top speed and then not go any faster. Speed, size, and shape. Okay, so the faster we go, the more air we have to push out of the way, the more resistance we're going to experience. Size. The bigger the object is. I mean, this object has to go through the air. It's going to have to push a channel of air out of the way that's that tall. This one is going to have to push a lot more air out of the way to get through that same trip. Okay? So the size is certainly important. Likewise, the shape. If we're going through the air and we're in a box shape like this, that's not going to make it easy for the air to get out of the way. It's going to try to go over and under and around the sides. And when it does that, and it goes over, it's going to do this little loop-to-loop action. Call it turbulence. And that's going to make friction. It's going to make it hard for that van or that double-decker bus to make it through. If the vehicle is shaped more like a wedge, now it's easier for the air to slide up over the top. You still get some of that little turbulence, but not nearly as much. So that won't slow it down as much. That won't be as hard to push through. Okay? You might have seen that on the freeway, you see the big semi-trucks, you know, and this is the cab part of the truck, and this is the tractor-trailer part of the truck back here. And sometimes they have these things that go on top of the cab that look like that. You guys know what I'm talking about? Okay, and that's intended to make it easier for the air to get over the top of the cab and over the trailer part so that it's not slowed down too much. So speed, size, and shape are all important factors. We see trees blown down in windstorms because of all the foliage, all the green stuff here. Works like a sail, and it just captures all that air. If this didn't have any leaves on it, air could go through, less likely the tree would be torn down. Okay? The shape is hugely important. So let's get to this demo over here.
So when asked the question if heavier things fall faster than lighter things, many of you said, yes, they do. Galileo, the third from the left above the board there, conducted an experiment on just that very thing. He dropped two spheres from the top of the Leaning Tower of Pisa. One was much heavier than the other, but they had the same size and shape. And what he found is that they both fell at the same rate. Gravity is a constant, 9.8 meters per second squared. All objects accelerate at the same rate, assuming they have the same size and shape, the same amount of air resistance. If you factor in air resistance, then you can make the right prediction. Here on Earth, if I were to drop this hammer from this height, many of you predicted the head would hit the ground first. In fact, you'll see that the hammer will fall straight. It won't turn over so that the heavier end falls first. Heavier objects are not pulled down faster. We often confuse the weight of the object with the force that it applies to the ground. If you were to drop this hammer on your toe, obviously that's going to hurt a lot more than a penny, not because it's falling faster, but because it has more mass. Force equals mass times acceleration. The penny may be going at the same speed, but it's the force from the mass that causes the pain in my foot. So heavier objects do not fall faster. What is important here is the size and the shape, because the size and shape of this part of the hammer presents a very similar size and shape to the handle. It won't cause the hammer to turn over in either direction. take a piece of paper and you crumple it into a ball, the piece of paper in the ball shape will hit the ground first. Again, not because it's heavier. The two pieces of paper have the same mass. The difference, again, is shape. In order for this to reach the ground, it has to push a cylinder of air about that big out of the way to reach the ground. This piece of paper has to push a much larger box of air out of the way. If you look at these two, many predict that the book will hit the ground first, and they say the reason for that is it is heavier. Yes, the book hits the ground first, but not because it's heavier. If that were true, then, when I put the paper on top, it should now fall the same. I haven't increased the weight of the paper. The book is underneath, they're not attached, and now you can see the two fall at the same speed. The reason the paper fell slower than the book has nothing to do with even the size or shape. They have a similar size. I shouldn't say it has nothing to do with the shape. It does have something to do with the shape, because as the book falls, the book is able to maintain its shape and stay flat, pushing the air out of the way in all directions. The paper, on the other hand, cannot maintain its shape, and it bends so that the air can rush around the sides. Once the paper is in this shape, it causes it to move sideways as it falls. And we all know the shortest distance between 2 points is a straight line. So the reason the paper falls slower than the book is not because it's lighter, it's because of its shape and the fact that it can't maintain a rigid shape to push the air out of the way.
Heck is that?
So, this next one, I don't know if there's enough space for me to do this here. I'm going to give it a shot. Two identical spheres. One's going to sit here on the little ledge. One's going to be released. And when I flip that lever, one will hit the computer screen. I hope not.
Can I catch it?
Over here. What we want to do, this happens pretty fast, guys. So what you want to do is listen for it. Listen for the sound of the ball as it hits the ground. Okay? One's going to be propelled out. And one's going to drop. Ready? Oh, which one's going to hit first?
The one that's over there.
Ready? 1, 2, 3. 3. Same time.
That's pretty
Same time.
Where'd it go?
When I learned this one, this really blew my mind. I had a hard time accepting this. That a ball being dropped at the same time that one's being thrown out are going to hit the ground the same time. The force applied to this ball that was propelled out was not a force against gravity. It went parallel to the earth. So that force propelled it this way. It had nothing to do with the ball falling. Gravity still works on this ball the same as it does on this one. So for every second, as this one was going down every second, this one was going down likewise, the same amount. It just was going to wind up further that way. Does that make sense? No. I agree with you. It didn't make sense to me either. And it really bothered me when the teacher said the whole bullet thing. That if you fire a gun and it's perfectly level to the ground, and you drop a bullet at the same time you fire that gun, that bullet will hit the ground the same time the one shot from the gun will hit the ground. The difference is this bullet will be a lot farther that way. Because that's what the force of the gunpowder did. It sent it that way. Now, would that be true if I fired a gun up and dropped one at the same time?
No.
No, because this force is against gravity. But gravity doesn't suddenly ignore things just because they're going this way. You know, when you pitch from the pitcher's mound to home plate, and you feel like, you know, or even if you play catch, you throw the ball hard to somebody from a distance, and you feel like the ball's going straight like this, is it?
No.
No. Every time, even when you throw it hard, it's doing this. Gravity's a powerful force, and it's going to pull things down. If you want to fight gravity, you got to aim up, right? And it's still not going to go straight up like this and go straight down. You throw the ball up in the air, it's going to do a curve every time. because gravity's working on it the entire time, from the moment you release it, okay? All right, the last one here is the washer drop. What do you expect the sound to be? Will it stay the same, speed up, slow down? Well, let me ask it this way. Which washer will have the most time to fall? The top one. So which one will be going the fastest when it hits the pan? The top one. So you got to listen carefully. 1, 2, 3. It's kind of hard to tell. It does speed up. It gets going faster and faster and faster. This washer is going to be going a lot faster when it reaches the pan than the bottom one. The bottom one only had, a tiny bit of time to speed up. Maybe it was going 9.8 meters per second. The top one was going faster than that because it was falling for a longer period of time. Does that make sense? One was going